All right, now this section starts out with what may seem like a detour, but we'll see in fact it's very relevant to what we're talking about, the idea of binary relations. I'm going to talk about partitions. All right? So what is a partition? Intuitively, I'll just draw the picture over here. If I have a set A, which I can represent as a box, and A has elements within it, which I'll represent as points, a partition is just a division of those elements into smaller sets. So for instance, I could divide these sets, take that set and that set. And so here I've partitioned A into 3 subsets. So A has 1, 2, 3, 4, 5, 6, 7, 8, 9 elements, which I've partitioned into 3 subsets. Mathematically, we can write that this way. A partition, which I'll denote by this letter script P, of a set big A is a collection of non-empty subsets of A. You see here I have 1, 2, 3 non-empty subsets of A, such that each element of A is in exactly one of the subsets of P. But you can see if I choose some element of A at random, I'll just choose a random element. Here's a random element, yep. And there's exactly one of the 3 subsets that that element is in. We could say that in a different way as follows. The union of subsets in P is all of A. That means that every element of A is in at least one subset of P. And the subsets of P are pairwise disjoint. That is, the intersection of any 2 subsets is empty. That means that any element of A is in at most one subset of P, because if it was in 2 or more subsets of P, it would be in the intersection. So A says any element of A is in at least one subset in P, and B says any element of A is in at most one of the subsets in P. So be careful here. This P is a set of subsets. The elements of P are subsets, which may contain multiple elements of A. Let's see some examples below. Consider the set of real numbers, R. Okay? Every element of R is either rational or irrational. Okay? So we can define 2 sets, the set of rational numbers and the set of irrational numbers. The union of these 2 subsets, Q union I, is all of the real numbers. Okay. On the other hand, Q and I are disjoint sets. There's no number that's both rational and irrational. So we've met the 2 conditions up here. The union of these 2 sets is all of R, and the intersection of the 2 sets is empty. So this collection of 2 sets, Q and I, is a partition of R. So notice that the elements of the partition are sets. We also sometimes use the word partition as a verb, so we can say that Q and I partition R. All right, now we could do something similar with the even and odd integers. The even and odd integers together, if you take the union of those 2 sets, you get all the integers. So we could say the even and odd integers partition Z, or we could say we could let P equal EO. So P is a partition. Another example. Let S be the set of all single element subsets of Z. Okay, so take every subset of Z that has a single element. 1, 5, 555, and so on. Now, clearly, every one element subset has no intersection with any different one element subset. And if I take the union of all one element subsets, it's going to give me all the integers. Okay, so this set of single element subsets is a partition of Z. So I could write S equals the set, well, 0 is in S, 1 is in S, 2 is in S. I'm writing these as sets because these are single element subsets, dot, dot, dot. But that's not all. Sorry, I should have made that a set bracket. Minus 1 is in S. The set consisting of minus 1 is in S. The set consisting of minus 2 is in S, and so on. Okay. So the set of all these sets is S and is a partition. I'm sorry, the set of all these sets is P. Sorry, this should be a P. I'm sorry, again, I said that wrong. S is the set of all single elements, subsets of S. So S is the partition. S is this collection of single element sets. S is the partition of Z. All right, here's another partition of the complex numbers. We can partition complex numbers according to their real part. Okay, so we can say, let RA be the set of all complex numbers with real part A. So what would that set look like? Well, if I take the complex numbers, and here's the real axis, and here's the imaginary axis, if I take some number A, some real number A, then what numbers in the complex plane have this real part? Well, if you think about it, if I do A plus I, which would be up here, that has the same real part, A plus 2I, A plus 3I, A minus I, A minus 2I, and so on. If you think about it, any number on this line will have real part A. Now, if I choose a different real part, I'll get a different line. Okay? So for every possible real part, I get a different line. So all these vertical lines. Now, if all these vertical lines are disjoint, and if I take the union of all vertical lines, I get the entire complex plane. So these vertical lines form a partition of the complex number. And each vertical line is indicated in this notation by R sub A. Okay, so what are partitions? Partitions are simply breaking up sets according to some classification. Here's one example. If you have Lego bricks, you could sort them by color, shape, number, or so on. And that sorting amounts to a partition. So here are some more examples of partitions. You can partition animals in a zoo according to species. You can partition people according to their given names. Every person has a given name, and a person doesn't have two different given names. At least in the United States, we don't do it that way. So every set in the partition consists of all people who share a particular given name. Okay, in geometry, sometimes we're only interested in the shape of a triangle and not its location or orientation, so we can talk about congruent triangles. For instance, I can have a triangle that looks like this, and I can have another triangle that looks like this. These triangles are congruent. They have exactly the same shape. It doesn't matter what the orientation is or the position, they're congruent. Now, these are different triangles because they're different sets in the plane, but I can say that they have something in common. So if I think of all possible triangles, I can group all possible triangles up into subclasses of triangles that are congruent. Okay? So a partition is a grouping, and each group is a subset of the set being grouped. Okay? Now, I've been talking previously about relations. What do partitions have to do with relations? So let's consider a particular example. Okay, here we have A equals 1, 2, 3, 4, 5, 6, and partition these 6 numbers into evens and odds. So I can say A1 is the evens, so it's 2, 4, 6. And A2 is the odds, that's 1, 3, 5. Okay, then, suppose we use a 6-sided die to determine a random outcome where if we get an even number, we win $1, we get an odd number, we lose $1. So we don't care whether we get a 2, 4, 6, as long as we get an even number, we win. Okay, so in this way, rolling a 2, 4, or 6 are related because they all have the same outcome. Okay, similarly, if I roll an odd number, I lose. I don't care which odd number it is, so all odd numbers in this example are related. Okay. So we can define a relation as follows. Given any two elements of A, those two elements are related if they're both even or both odd. Okay. So to draw this picture here, I've got my set big A. I've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. And 1, 3, and 5, these 3 are related. And 2, 4, and 6 are related. you can see I actually have a partition. 1, 3, and 5 is one set, the 2, 4, and 6 is another set. Their union is all of A, and their intersection is empty. Okay. So, given any partition, we can define a binary relation. Okay. Two elements of the set A are related if they're in the same subset in the partition. All right then, we've established that partitions give rise to relations. And the next question we can ask is, do these relations have any special properties? Oh, let's see what we have here. Let's go to this picture here, which shows a partition. Okay, so here we have a big set A, and we divided that into 5 subsets, A1, A2, A3, A4, A5. And so all the elements of A are in one of these sets. Here's A1 and so on. And remember, we define the relation is if 2 elements are in the same subset in the partition, they're related. So for instance, A is related to B and vice versa. Now we can notice some properties of this relation. First of all, every element of A is related to itself. Right? For instance, D is related to D. Why? Because D is in the same set as D, so we have to say D is related to D. We didn't say relation has to be a different element. We just said that 2 elements are related if they're in the same subset in the partition. And obviously, any element is in the same subset of the partition as itself. This property is called the reflexive property. And this is a property of relations. On the other hand, we can see that if 2 elements are related, then the relation goes in the other direction as well. Now, you know this is not true for all relations. For instance, if you have the relation less than, A is less than B does not necessarily imply B is less than A. In fact, quite the opposite. But if you look at this picture, if I have 2 elements that are related, say H and I, if H is related to I, then I is certainly related to H, because I can argue it both ways. But this property that A related to B implies B related to A is called the symmetric property. Right? One more property is called the transitive property, and that's a little more complicated. Let's look at this set here. And we notice that A is related to B, and B is related to C. Well, it just so happens that A is also related to C. Now, why is that? Because A and B are in the same set, B and C are in the same set, so A and C must be in the same set. So you can see that this must be a general property of the relation that comes from the partition. Okay? If I have an element A that's related to B and an element B that's related to C, then A must be related to C. This is called the transitive property. All right. So this partition that we show here has definitely a relation that exhibits these 3 properties. Reflexive, every element is related to itself. Symmetric, if an element is related to another element, that element is related back to the first. And transitive. If I have 3 elements, the first is related to the second, and the second is related to the third, then the first is also related to the third. Okay, so here we investigate some other partitions and the associated relations, and we can verify that, in fact, for these other partitions, we still have the reflexive, symmetric, and transitive properties hold. So you can read through this example, and there are also some exercises that show the same thing, that you're supposed to show the same thing. The upshot is that whenever we have whenever we define a relation, this shouldn't say that, okay? Whenever we define a relation from a partition, that relation seems to have these 3 properties. Right? So here's how we state that proposition formally. Given a partition P on a set A, define a binary relation of A as A is related to B if and only if there exists a subset in the partition such that A and B are both elements of C. In this case, then the binary relation satisfies the following three properties. It has to be reflexive, it has to be symmetric, and it has to be transitive. Now the proof, in fact, when we made this discussion here for this particular partition, we didn't use any particular properties of this partition in our argument. When we talked about little a and little b as elements of A, big A, we didn't refer to specific elements. So in fact, this is a general proof that will work for any partition of any set A. Right? So that's our proof of this proposition. Let's see. Now there are some pitfalls. Oh, before we talk about the pitfalls, recap. We know that any partition gives rise to a relation that's reflexive, symmetric, and transitive. So we're going to call that type of relation an equivalence relation. Any relation that satisfies these three properties, reflexive, symmetric, and transitive, is known as an equivalence relation. So the proposition that we proved, we can restate as follows. Given any partition P on a set A, define the binary relation as follows. A is related to B if and only if there exists a C, which is a set in the partition, such that A is in C and B is in C. In other words, A and C are both in the same set. That's the same thing as saying A is related to B. If this is true for your partition, and you define this binary relation, that binary relation is an equivalence relation. Now here's some examples where you will look and see the properties of relations that you're familiar with. In fact, equality is reflexive, symmetric, and transitive. Less than is transitive but not reflexive or symmetric. Now the way to show that a relation doesn't have a property is show a counterexample. Okay, only one counterexample is enough to disprove a property. Okay? Because if a relation is reflexive or symmetric or transitive, it must be reflexive in all cases. All right, so we give more examples where you're supposed to show reflexive, symmetric, and transitive. All right, so here's some examples that you should look at. I'll just say something here. For instance, this relation here is actually transitive. Why is that? Because transitive says if A is related to B and B is related to C, that implies A is related to C. Okay, this is what transitivity says. Now, is this relation transitive? Well, if it's not transitive, there must be a counterexample. There must be a way to show that it's false. If the only way to show it's false is give me an A related to B and a B related to C. Now here I have 3 related to 1, so that's my A related to B. Where's my B related to C? 1 isn't related to anything. So the point is that I can't fulfill this condition, so I can't find a counterexample. This relation is transitive, okay? Because whenever you have one relation, which corresponds to an arrow, followed by another relation, which corresponds to another arrow, then I have the direct arrow from the first one to the last one. Okay? Since I don't ever have 2 arrows following each other, I never have a failure of the transitivity condition, so transitivity holds. Here's another example where the relation is transitive. Notice I have 3 goes to 1 and 1 goes to 2. So this says 3 is related to 1, 1 is related to 2. And I find that, in fact, in this case, 3 is related to 2. So the transitivity condition holds for that particular triplet of numbers. Now, to be transitive, it must hold for all triplets of numbers. And the reason it holds for all triplets of numbers is that that's the only case where you have one relation followed by another relation. For instance, if I try to apply this for 3 related to 2 and 2 related to 1, well, I don't have this condition satisfied. If I don't have this condition satisfied, I don't have to worry about whether this condition holds. Transitivity just means if I have one arrow followed by another arrow, then I have a direct arrow that links the first to the last. So you can read the discussion. This is a sticky point that trips up many students. So take some time to understand these 3 examples. Okay, so we're giving you some practice to understand these 3 concepts: reflexive, symmetric, and transitive. And we'll stop there.